Tracking the exact state of a particle moving through a chaotic environment using classical mechanics requires a constant second-by-second accounting. You have to know every force, in every direction, at every infinitesimal moment. Newton's second law is built on vectors, quantities defined by both magnitude and direction. To predict a final state, you must track these multidimensional arrows as they constantly rotate and stretch across the particle's path. This approach becomes computationally overwhelming for any system more complex than a straight line. Every twist in the path adds another layer of vector calculus to the ledger. It raises a logistical question. Is it possible to determine an object's final speed by looking only at where it went, without needing to calculate exactly how long it took to get there? To simplify the math, we need a model that eliminates time as a required variable, focusing instead on the spatial journey itself. We can achieve this by using energy, a scalar quantity that tracks the total amount of motion potential rather than the specific direction of the travel. Unlike vectors, which are tied to a coordinate system, scalars are pure magnitude. They tell you how much without caring about which way. This shift requires us to bypass the clock. Instead of measuring what happens per second, we measure the total impact of a force over a specific distance. We use terms like work and energy casually to describe human stamina, as seen here in these long-distance runners. But in physics, these terms describe a very specific mathematical relationship. When we calculate the total force exerted across a spatial displacement, we derive the work-energy theorem. This theorem provides a framework where time is secondary. It shows how mechanical energy is exchanged and maintained within a system based purely on its configuration and motion. To transition from directional forces to directionless energy, we first need a way to multiply two vectors to get a single scalar value. This operation is known as the scalar product, or the dot product, written as A dot B. The formula for a dot product is the magnitude of A times the magnitude of B times the cosine of the angle theta between them. Geometrically, this is a projection. If vector B were to cast a shadow straight down onto vector A, the length of that shadow represents the part of B that is actually aligned with A. This isolates only the specific component of the second vector that runs in the same direction as the first. The dot product is simply the multiplication of these two newly parallel magnitudes. By using the dot product, we strip away conflicting directions and produce a single scalar magnitude that is much easier to track. We apply this math to the physical world by looking at the relationship between force and displacement. Work is defined as the dot product of the force applied to an object and the displacement it undergoes. If you pull a block with a rope at an angle, only the portion of your force pulling parallel to the floor actually does work to move the block forward. The upward portion of your pull is effectively ignored by the displacement. This leads to specific rules. For instance, what happens if there is no spatial displacement at all? This weightlifter exerts massive force holding the barbell stationary, but because the displacement is zero, the physical work done on the load is zero. What if the force is perfectly perpendicular to the motion? Because the cosine of 90 degrees is zero, the Earth's inward gravitational pull does no work on the moon as it moves along its circular path. The force and the motion are at right angles. When work is done, it changes an object's motion. Since work is force, or mass times acceleration, acting over a distance, the energy accumulates as the square of the speed. We call this kinetic energy, half the mass times the velocity squared. This unit of energy is the joule, named for James Prescott Joule, who helped define the link between mechanical work and heat. The net work done on a body is the exact amount by which its kinetic energy changes. In most real-world scenarios, forces aren't constant. They fluctuate based on the object's position. This chart shows a force that changes as the object moves along the x-axis. To calculate the work done here, we have to look at the area under the curve. We approximate this area by breaking the displacement into small segments. In each segment, the force is roughly constant, allowing us to calculate a tiny bit of work. As we make these segments infinitely thin, the approximation becomes exact. This process is integration. The resulting area is the total work done by the variable force over the entire distance. Mathematically, work is the integral of force over displacement. This calculates how much energy a falling raindrop loses to air resistance. even though that resistive force changes depending on the drop's speed and position. Integration provides the tool to track scalar energy even when the environment is in constant flux. Not all work goes into immediate motion. Energy can also be stored within a system's configuration. We call this potential energy. This only applies to conservative forces, like gravity or springs, where the work you put in can be recovered later as kinetic motion. The force in such a system is always pushing the object back toward a lower energy state. This means the force is the negative rate at which potential energy changes as you move through space. Consider an ideal spring. Pull the block from center, and the internal force pulls back in the opposite direction. Stretch it further, it pulls harder. On a graph, this forms a straight line. The work to stretch it creates a triangular area under the line. That work is stored as elastic potential energy, defined as 1/2 the spring constant times the displacement squared. Conservative forces act as a recovery system, holding energy in place until the system is allowed to move. Release the tension, and the stored potential energy is instantly converted. The banked energy is traded back for pure kinetic motion. In a closed system, any loss in potential energy is matched by an equal gain in kinetic energy. The changes balance out to zero. The sum of these two values is the total mechanical energy. When the forces doing work are conservative, this total energy remains constant. It doesn't matter how complex the path is. The total remains the same at every point. Non-conservative forces, like friction, turn some of this mechanical energy into heat, but the underlying logic of the energy ledger remains the same. By looking past the complex vectors of Newton's laws, we find a simpler, scalar world where motion is a perfectly balanced exchange of energy.